Thank you very much. So my presentation here is talking about Windows Vista resource virtualization, specifically about some of the bugs I found in it and a bit of exploitation of some interesting bugs that I found in the last couple of months. So I'm not going to introduce myself more than that. I work for Project Zero. I tend to find Windows vulnerabilities. That's my main area of interest. And I primarily look for privilege escalations. So these sort of resources, this resource virtualization is a perfect place for me to go hunting for bugs. But why was resource virtualization needed? I'm going to go into that in a little bit. I'm going to then talk about more in depth about how the resource virtualization is implemented. And then, of course, bugs, because bugs is the most interesting thing about this, right? So let's go into a bit of history. If you've used Windows ever, is the colors right? Oh, okay. If you've used Windows since Vista, you'll almost certainly seen a dialog like this, or at least a variant of this dialog. And this dialog is UAC. This dialog basically is the operating system warning you that an application wants to run with administrative privileges. And it goes, hey, can I annoy you to click yes? And most users will probably go, sure, I don't know what this is doing, but I'm going to click yes anyway. So it's a fairly ineffectual security boundary, and of course Microsoft do not support it as such. But if you read Mark Rusinovich's TechNet article about UAC and why UAC was introduced in Vista, pretty much the first line in that text is UAC is meant to enable users to run with standard user rights as opposed to administrative rights. And I think this is a bit of a retcon on Mark's in Mark's terms, because I think it originally was designed to be possibly a securable boundary, but of course it turned out to be virtually impossible, and so he retconned it into a developer feature to make things work better, right? But anyway, that is the stated aim of UAC, and that's kind of like what a lot of the features of UAC are based around. But of course UAC introduced numerous problems. This was not the only problem, but one of the big problems was backwards compatibility. You've got all these legacy applications written for Windows 9X, which had no resource security at all. So when I talk about resources, I mean files, registry keys, all that sort of stuff. It has effectively no security. And that's by design. It came from MS-DOS. It was purely a consumer operating system, single user. There was really no need to have some sort of resource security, because basically the only attacker really was the local user who already had full control. That's slightly different though in the sort of more enterprise branch, Windows NT. This was built from the ground up to have security. Some may scoff at that term, but Windows NT was a secure operating system in the sense of you could have multiple users. There was fine-grained access control between users. The trouble was, certainly at least when it was deployed for consumer usage, so sort of Windows XP and onwards, everyone was an administrator. So the first account you installed when you set up your copy of Windows was always an administrator. And effectively, that's no different from the 9X scenario. You effectively have no resource security because pretty much every resource is accessible to an administrator. And what this meant from a legacy application perspective, and certainly from a backwards compatibility perspective, was applications assumed they could do anything on the system. They could write to anywhere. They could modify anything they liked because they were always allowed to. But of course, UAC comes along, and everyone's now running as a standard user, not as an administrative user, and all of a sudden it stops working. And as ever with big OS projects, if the OS is breaking perfectly working applications from the user's perspective, it's clearly Microsoft's problem. That's never a good sign. Oh. It's clearly Microsoft's problem as to why it's failing, and not, of course, the shitty application which caused it. So Microsoft's solution in this particular part was to do something called resource virtualization. And when I talk about virtualization, I'm not talking about in the sort of the current usage where you're virtualizing an entire operating system. This is purely to virtualize the presence of specific resources, namely file resources and registry resources. And for all intents and purposes, if you had what was nominally a legacy application, if it tries to modify an administrative-only resource, then the operating system would do something to pretend, to maintain a fiction that, oh yeah, you can write to that resource, there's no problems. But of course, in reality, it's not really allowing it to do that. And by implementing this, in theory, it solves most of the backwards compatibility issues because, for all intents and purposes, these applications don't realize they're being virtualized. So let's go into a bit more of a nitty-gritty of actually how this works in Vista. It's worth noting that I'm talking about Vista here, but of course, this code is still there in Windows 10, the latest versions of Windows 10, and all my bugs, which I'll present later, all worked all the way up from, basically from Vista, all the way to the latest versions of Windows 10 when they were patched. So if you bring up Task Manager, it's not on by default, but you can open it and select the column options, and one of the column options is IIC Virtualization. And this shows the state of whether an application is virtualized or not, specifically resource virtualized. And it turns out if you do that, you'll notice that there is three states, three possible states. There is not allowed, there is enabled, and there is disabled. And this is just a task manager on a default install of 32-bit Windows 10, and I think it's like 1809. And you can see that even on a default install, there are system components which are running with virtualization enabled in a modern version of Windows, which seems kind of crazy. Isn't it only for legacy applications? Well, mostly. Your task manager also gives you the option to toggle it. If you want to toggle it on an existing application, you can do if you want to. But where is that information coming from? The information is actually stored inside the access token for a process. So each process on the system has an access token, which is your user identity. And inside that is some flags. And there's actually two flags. So rather than like a tri-state flag, it actually has two separate flags. One which says whether virtualization is allowed or not, and one which is whether it's enabled or not. So this is just set, but there's also the equivalent get, that token information. So this is just set by an application. And in the kernel, if you go looking at the code, it's very simple. If you're disabling it, it just clears this flag. If you're enabling it, it will only enable that enabled flag if virtualization is allowed. And the idea here is that, of course, certain types of user shouldn't be virtualized because they shouldn't be running like legacy code. So things like system services, they should just either be running as an administrator anyway, or you probably don't want system services which are doing unexpected things to the operating system. Also, like if you're a UAC admin, so if you're running as the standard user in UAC, you can be virtualized and this is allowed. But if you're not, if you're running as the administrative user, then of course that's not, the virtualization is no longer allowed at that point. Now you may think, okay, how does this get turned on? Well, Microsoft obviously went, well, we need to kind of enable this by default, but of course we don't want to enable it for everything on the system because that would probably cause more problems. It wouldn't allow application developers to fix their code because the whole point of this nominally is that it's a band-aid to stop these developers having to fix their code up until a certain point. And once they reach that certain point, they say, well, you need to change your code, otherwise it's not going to work. So as part of the process creation routine inside user mode, so this is not actually in kernel mode, it basically does a very simple check after it's created the process. It goes, is it running 32-bit x86? And so this is 32-bit x86 application. So if you're on a 64-bit system, these are anything which is running under the WoW64 virtualization tricks to make 32-bit work. Of course, if it's on a 32-bit OS, then everything is normally 32-bit, so this check doesn't apply. And then, does it have something called a manifest? And a manifest is an XML file which is usually embedded inside an executable and says things like, do I need to elevate this process to administrator? So this was really primarily introduced in Vista. It was kind of introduced earlier, but it was like first sort of like made mandatory for Vista applications. And so the definition of a legacy application for Windows is, does it have a manifest? If not, is it 32-bit? If it is, we'll turn it on automatically. And so you can see this, those applications which are running without virtualization, they're with virtualization enabled. Those are all applications which, even though they're installed as part of the operating system, they're running 32-bit and they don't have a manifest. So even though they're actually Microsoft signed binaries, they're considered to be legacy applications and virtualized. It's kind of interesting. So ultimately, I can just hopefully show this. So actually, these flags are very easy to see. Of course, if you've got the tools to do it. So this is our current access token. And it obviously contains multiple pieces of other information that we're not that interested in. But if we look under the miscellaneous stuff, we can see that just here, like in the middle, there's the virtualization allowed flag and virtualization enabled flag. And because this is a allowed application, we can obviously toggle that on and off. And it's worth noting that even though I talked about x86, 32-bit x86 applications is the only one which get virtualized. That is true in the sense of those are the only ones which get automatically virtualized. However, you can turn this flag on for 64-bit applications. You just have to do it manually. So any of these vulnerabilities I will present later on, these vulnerabilities I discovered, can still be used on a 64-bit system. You don't need to run a 32-bit legacy application. You just need to toggle this flag on the access token, and it will all work for you. So let's go into actually more depth of how the individual components work. So we'll start with registry virtualization, because that's relatively simple. Both registry and file virtualization have sort of common like design elements, but they are actually implemented in different ways. So both file and registry virtualization have the concept of a virtual store, and this is basically a location inside the user's own, in this case, the user's registry hive, which obviously the user can write to, the normal user can write to, which is used to store the virtualized registry data. And so in this particular case, we see on the left that there is this virtual store key, and that under that key has numerous other keys which are indicative of things which have been virtualized automatically. So the basic principle of how registry key virtualization works is something like this. So if you try and create a key in the local machine hive, so the administrative only registry hive, of course, in a default case, if you haven't got your application is not virtualized, then it's going to give you access denied. It's going to go, well, you can't create that key. You're not an administrator. You're trying to create it in an administrative only location. Access denied. Sorry, goodbye. And of course, that's exactly the problem of legacy applications. They're trying to create these registry keys in local machine, getting access denied, and either blowing up because they never expected it to even fail, or at the very least, just stop working because, oh, I couldn't write my configuration key, therefore I'm just going to completely bomb and stop working properly. So what the registry virtualization does is if you've got this turned on, if you try and create that ABC key in local machine, at least in the default sense, it will go, okay, I can't create it in the machine hive. I tried, it gives me access denied. So instead, I'm going to redirect that access to the user's virtual store and then create it in there. And then at that point, that registry key is, for all intents and purposes, virtualized. From the application's perspective, it created HKey local machine /ABC, but in reality, it created this virtual store key. Now, of course, the operating system then has to maintain this fiction, but yes, it really did create the local machine ABC key, because if it doesn't, bad things can potentially happen. Now, you can't probably see this too well because the color's a bit washed out, but basically, this is demonstrating that fiction. So when you create that key, I said I wanted to have all access to that key. And this turns out that this key already exists. So this is the Microsoft key. This is always there in local machine. And of course, creating keys are one thing, but of course, if you're trying to open an existing key, you have this interesting problem that you have to support all the data which is already in that key, but you also have to kind of make it writable. So the trick that the registry virtualization does is it kind of just lies to you. It says, okay, you asked for write access, normally, on that key. You can't have write access, but I'm going to pretend you got write access. However, if you actually enumerate what access was granted, you actually only get read access to that key. And therefore, other components then need to, again, maintain this virtualized fiction along the way. So this is how it does it. So this is, for example, when you're trying to set a value in one of these virtualized keys. Now, the common pattern for Windows system calls, you pass in a handle to an object, in this case a registry key, and it will try and convert that handle to a pointer to the kernel object which represents that resource. And in order to mediate access to that resource, it says, make sure that this handle has set key access, the set key access bit, and return me the pointer. Otherwise, return me an error code. So of course, in these virtualized keys, you've only got read access. You do not have set value. That's a write access. So of course, this fails. This goes, nope, sorry, you can't do that. You do not have the correct access right. However, the actual kernel code itself goes, right, okay, I've failed. I've been told I have access denied to this registry handle. Are you virtualized? So it does a check to make sure, are you actually a virtualized application or not? If you are, I'm going to reopen that key for read access and then create basically a new virtual store key for that backing data. Because basically, once you've done this, you can create the real virtual store key. And this is where actually you're going to start writing these values to. You're not going to actually write them to the real registry key because that would kind of defeat the object, right? Like if you could write to the real HKey local machine key, well, you've just bypassed security. So of course it needs to, at this point, go, right, okay, make sure we have a virtual store key to write to, switch around the pointers a bit so that we actually write to the correct location. Now it turns out Microsoft realized, well, we don't want this to apply arbitrarily. For example, this only really works for the software hive. When it gets loaded, it has a specific flag set which says this registry hive can be virtualized. And as the majority of applications wrote to the software hive, it was decided, well, we'll just limit it to that, right? But of course, each key then also has a set of flags which have modified the virtualization behavior. Now the top one is basically, am I allowed to virtualize this key at all? And so certain parts of the registry will actually have this flag set which says, nope, you cannot virtualize this key. So for example, the Microsoft key has this clear, which means that you can virtualize the Microsoft key. However, the Microsoft Windows key underneath it has it set, which means that if you try and create virtualized entries in the Microsoft the Windows key, it just fails. The second flag is related to that open. So when you open it, if that flag is clear, it will then do that dirty reopen to fake out the fact that it's actually virtualizing the key. And then the final one just is basically, should we recursively create new, pass these flags on whenever we create new subkeys of this key, which is usually clear, but of course sometimes it's set. Usually it's set if you want to propagate the don't virtualize. So It's relatively easy to demo that. If I get my access token, hopefully. So at the moment, virtualization should be disabled. So it's currently false. And of course, if I try and create a new key in registry/machine, software ABC, then of course I get my access denied. It just goes, nope, nope, you can't do that. But if I just now do virtualization enabled, this should now actually succeed, hopefully, yeah. Now, as far as it can tell, it is actually the software ABC key. And because this is actually being created, we should have also been granted full access to this key. But if we now look under HKey current user, software classes, virtual store, oops. Classes. Okay. Apparently it doesn't exist. I'm not even sure how that works. Let's go for regedit, because regedit's usually a better working thing. Software classes. Yeah, okay. So hopefully you can probably see that it's now created an ABC key under our virtual store, which is now, and if you actually write to that key, of course, even though it claims to not be where it is, we should be able to actually see that replicated in here. And there we go. So it all kind of works. And as far as the application can tell, it's clearly not virtualized, and it's all working perfectly. Okay, let's go on to file virtualization. So file virtualization, registry virtualization is all done inside the kernel. So the kernel itself is modified to change the registry behavior. However, file virtualization instead is done using something called a filter driver. So in Windows, it supports the concept of having a driver which basically can filter I/O request operations. So you have your I/O manager on the left here, which is doing like creating files, writing to files, and that generates some sort of I/O request which gets passed across normally to the, say, the NTFS driver, to the volume. And in the middle, you have this Lua FV. Lua is like least user access, which is the old name for UAC. And things obviously get baked into Windows eventually. And this implements code which can basically see these I/O requests as they go across and filter out or modify or complete these operations where necessary. But fundamentally, it works in basically the same way as the registry virtualization. You try and create, say, a resource in a location which is normally administrative only, say the Windows folder. And of course, normally it would give you access denied. But of course, if virtualization is turned on, then creating abc.txt under Windows will actually create you abc.txt in the virtual store location. But of course, how it does that is subtly different. So normally, if virtualization is disabled, it will still go into this filter driver. And that's because the filter driver just sits there, constantly churning away. So whenever you make any file request on Windows, and people complain now, whoa, Windows is really slow. Well, the amount of rubbish they put in front of just a simple create recall is ridiculous, right? Because like literally on a modern version of Windows 10, this is still intercepting every single I/O request you make to your file system. Seems kind of crazy. But in this particular case, one of the things the filter driver can do is it can say, is this request a success? Have I completed operating on this I/O request? And it can also say, do I need to know about the result of this operation, or can you just continue on and do it? And of course, if you're not virtualizing, it goes, okay, this application is not virtualized. Come what may, if you're trying to write to Windows, you're going to fail, but I'm just going to let you, right? So it says, don't ever talk to me again for this file request. I don't care anymore. And of course, then the I/O manager can just talk to NTFS directly, do the actual create operation, either works or it doesn't work. But another thing the filter driver has to do is it goes, okay, if it's actually virtualized, is there an existing file which I've already virtualized that I need to actually handle? And so it will actually check inside this virtual store, which is on a per user basis. It'll say, is there an existing file that this virtual store already has, which will satisfy this request for me? If it finds that, then what it does is it actually says, okay, to the IO manager, you know what, actually, you're not looking for windows/abc.txt. Instead, you want virtual store/abc.txt, please. Can you just try again? And it also marks that request with a special flag, which basically says, oh, and by the way, don't talk to me about this request again because I'm not interested. So of course, it then, again, the IO manager can just go straight to NTFS create, but in this case, rather than trying to open, say, the real file inside Windows, it goes back to the virtual store backing and then goes, okay, you can now satisfy that from the virtual store. The really interesting one, and the one which is most interesting from a security perspective, is something called delayed virtualized. And registry keys do it as well, but like it's kind of more important for files in many respects, because like I want to modify a file. And one of the actual bad behaviors of legacy code was not necessarily that they were trying to write to a resource. They were just not fully understanding what they needed to do when they were trying to open that resource. So for example, you may try and open a file in the Windows folder, and they only want to read it, but they ask for write access anyway, because they go, well, like, this is just how it works. And it works, right? It just doesn't give me an error, so like, what's the problem? Of course, that will now fail if you're running as a standard user. So what delayed virtualized will allow you to do is it will allow you to open the file if the file already exists, but at the point of open, it doesn't create the virtual store file because you haven't written to it yet. Instead, it delays that writing until some subsequent time before it needs to do anything. So of course, in this case, it says, right, okay, I don't know what to do with this necessarily. Make sure you call me back once the IO request is completed, so I can do something with the result. And of course, the result comes back, and in this case, the result is access denied. It says, sorry, you asked for write data access, but you can't have it because you're not an administrator. At this point, the file virtualization driver can go, oh, okay, well, how about I just open it for read instead? Like, is that okay? Yeah, good, awesome. Right, so it reads the file, and it just opens it for read access, not for write access, similar to the registry key virtualization. And at that point, it can pass that back. But unfortunately, because this is not inside the kernel, it's not as simple as just like lying about it in all the file operations. It is in the kernel, but it's not inside the kernel binary itself, so it can't sort of modify the behavior of the kernel. Instead, it's all done inside this virtualization driver, so it needs to be a bit more tricky. And what it does is it has, whenever you open a file, it creates a file object, and the IO manager allocates that file object, and normally that file object is populated by the volume driver, the NTFS driver. In this particular case, the virtualization driver opens the real object, but only for read access. So it opens abc.txt for read only, and then it creates this virtual file control block, which contains a pointer to the real file object. Contains a sort of an error status and a magic value which indicates that it's a virtualized file. And then the real file object it was created when the IO manager created the request is modified to add this pointer which points to this virtual file control block. And then at the bottom we got something called the section object pointers which are important in a little bit. So this is how the trick works. So whenever a IO request is made which passes through the virtualization driver, and this is why every single request gets passed through this driver, just on the off chance that one of these file objects is a delayed virtualized file. It has three checks. It first goes, is this a virtualized file or not? If it's not, I don't care anymore. Just go away, leave me alone. If it is a virtualized file, and we've opened this real file object, this read-only file object, well, let's just set the target file object for the rest of the operation to that object, and just say again, carry on, instead of using my current file object, use this virtual file object instead, this real file object. Otherwise, that means that some sort of error occurred during delayed virtualization, like if it can't write the virtual store file, for example, then of course it will generate an error status, at which point it would actually just say, right, I can no longer continue with this operation. This is a virtualized file, but it's clearly failed at some point, so automatic fail, set the error status. And so ultimately, unfortunately, the red seems to be washed out a bit there, but ultimately what happens then is if you try and open an existing file, it will open that file nominally. It will give you full access to that, and it has to, because otherwise the rest of the kernel doesn't work correctly. But it will not do anything until you write to it. And once you write to it, the callback operation in the virtualization driver realizes that you're trying to write to it and goes, oh, right, okay. Just before you get to actually write to that file, I'm going to switch that file around. I'm going to create the virtual store file, copy any existing contents from the real file into that new file, and then I'm going to basically switch it around. And so when you write to it, you now see that the full path which was originally for that file now becomes this virtual store file instead. So you kind of get this switching around. And that's what a completed delayed virtualized file looks like. Basically, you have your context pointer to put in your virtual file control block, which is basically the same. Those parts are the same. But now you've changed the real file object pointer to point to the read-write file, which we've created in our virtual store. And of course, again, these section object pointers get updated, which we'll go into in a second. So these are some of the operations which complete a delayed virtualized file. So the idea here is that any operation which could potentially write to that file, it needs to then create the virtual file before it allows that operation to continue. So writing data to a file, creating a writable section object, all that sort of stuff are all things which need to cause the virtualization to complete. A good example is creating a writable section. The filter driver gets this pre-acquire for section callback, and it says, okay, is the caller trying to create a mapped file view, a memory mapped file view for write access? And if it is, it calls that same pre-write function which would normally be called if you just call write, nt-write file. Otherwise, it just lets it continue because, of course, in order to maintain this fiction, it would make no sense that if you're only mapping it for read, that, again, there's no point virtualizing that file if actually all you're going to do is read from it. So we'll just let it continue and pretend that it's actually the real file all along, right? And that works. So there's clear virtualizable locations. These were obviously picked by Microsoft as the common places that people try to write to. Things like program files, the Windows folder, System32 folder. There are some quite substantial numbers of exclusions. So if you were playing with this, you need to obviously bear that in mind. I'm not going to put the whole list because the list is massive. You can find it in the virtualization driver if you go looking. And there's also banned extensions. So Microsoft decided, okay, we won't virtualize executable content. And this was clearly a conscious decision. So the majority of this is executable content like exes, VBS files, things like that. So if you try and create a virtualized file or access a virtualized file which has one of these extensions, it will also reject you outright. It will just sort of say, no, access denied to that file, and will do no virtualization at all. So again, it's pretty easy to demo. We're already running virtualized. So if I just close that just so I don't forget. Again, if I create a new file inside the Windows folder, we should find that it still works, because even though we would not normally be able to do that, because if we turn off virtualization, and we try that again with a different file name. It of course gives us access denied. So if we turn that back on, we see that actually, because this is actually being created automatically, the virtual store file is already created for us. This isn't delayed virtualization. This is actually just non-delayed. But of course, if we actually try and open instead, say system32 license.rtf, and give it a specific access, so generic write, for example. Oops. That's because I am an idiot. Okay. So now we can see that, of course, license.rtf is actually opened, but of course we couldn't really open it for write access, but we do apparently have write access. And then if you write to that file, it's going to virtualize it and it's all going to work as you'd expect, for the legacy application anyway. It maintains that fiction. Right, okay, let's talk about bugs, because bugs are the most important thing about these presentations. So there's actually 8 bugs here, which you can find on our issue tracker. The number on the left-hand side is the issue, it's the specific issue for the issue tracker. You may notice from the numbers that one of these is not like any the others. Like first one is issue 215, and then it starts at like 1700s. And that's because 215 was actually found when I was looking for a completely different bug class, specifically token, access token behaviors, bad token access. And so, of course, I found this a long, long time ago, and I never really bothered to fully investigate further some of the other features of virtualization. But all these are privilege escalations in one form or another. And I'm only going to concentrate on 2. I'm going to concentrate on one, registry virtualization 1, which allows you to basically read arbitrary registry keys without any access checking. And I'm also going to talk about one which is kind of an interesting race condition in the file virtualization, which allows you to modify arbitrary files. So let's talk about the registry key one first. So one of the other things that needs to be maintained from this virtualization fiction is if you open a virtualized key and you want to write to it, well, you can't just copy the entire contents of that key. That key may have multiple subkeys, which might have megabytes and megabytes of data. You're not going to copy all that into the virtual store, and you can't easily synchronize that if it changes. So what the kernel actually does is it merges the view between your virtual registry, the virtual store key, and the existing real registry key, which already exists in the registry. So when you do, say, query key, which does key enumeration, it will go, okay, I'm going to open the real registry key and merge those views together. So merge whatever keys are there, merge whatever values are there, so that, for all intents and purposes, it looks like you've written to the real key, and the real key has subkeys and all that sort of stuff. So if you actually look at the code for this, it's all, again, inside the kernel itself. It basically goes, okay, is this key the target of virtualization? Is it basically a key which is in the virtual store? And this is just set as a flag on the key control block. If it is, convert that key control block key to the actual real path that virtual key is representing. And then open that key by name, okay? And that in itself is not particularly bad. It doesn't maintain an existing reference to the real key. It instead opens it on demand. But there is a bug here, and the bug is that. The bug is that it's passing kernel mode as the access type to this reference object by name. And what that means from a Windows security perspective is it disables Windows security. Because it basically says, open that key, and whatever the access control of that key, just ignore it. I'm not gonna, just open it, please. Sort of like a desperation move, right? Please open it, right? Even though all the things leading to this point should have meant that the caller has read access to that registry key, and therefore this should just work anyway. It doesn't need to do this flag, but that's what Microsoft did. Now that in and of itself wouldn't necessarily be a problem if the only way to get that flag set which says this is the virtual key was like it required you to do full virtualization. But if you actually look at how this conversion to the real path works, it gets the key, it then says to the operating system, hey, give me the full path to that key. So this, of course, is a virtual store key, so it's under the user's hive, blah, 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 software ABC. And then literally the code just goes, right, okay, just get rid of the first 6 path components from that key path, and just slap on /registry, and there we go, there's your final path. So no checking is done whatsoever in this conversion process. So of course, you can change that to /machine/SAM, and of course, it's now going to open the SAM hive instead. And because the open is running as kernel mode, even though we can't open the SAM hive because we don't have access, well, it's going to allow you to enumerate the SAM hive for you. Now, of course, it's never quite that simple. Like if you just create that key in the appropriate location, it goes, well, this isn't the virtual store key, what are you talking about? And you may think, oh, okay, the only way to get this would be to virtualize the SAM key, but the SAM key isn't virtualizable, and we also can't write to it anyway, therefore it's not going to work. Well, it turns out that if you read the documentation, you'll see that all these things are reserved for system use, and of course, at least one of these is of particular interest to us. It turns out that one of those settings you can set on a key from user mode, so you don't need to have kernel mode access to do this. You don't need any specific access rights. I think you just need set value access on that key, which can be anywhere. You set virtual target equals 1, and it becomes a virtual store key. And that's all you need to do. So I have a very, very simple application here. So it's creating this virtual store key. If you give it a path, it will create a virtual store key. And then, of course, it will set this virtualization flag for you. And, of course, this is running a version of Windows which hasn't been patched. Otherwise, it wouldn't work, because it should now be patched. So we're going to create machine/SAM/SAM. It's mounted as the SAM hive, and then it has the SAM registry key underneath that. And if we now run that, oops. It'd help if I, what have I done? That's never a good start, is it? Okay, let's try this. Okay. I did actually test this, and of course, clearly I didn't. Yeah. Okay. That's because so the reason for that was because I had virtualization turned on, so it now tried to write to the SAM key, which of course it couldn't do, so it obviously failed. Sorry, I am clearly not paying attention. So if I turn back on virtualization now, I can, well, if that's off, then if I enumerate the key, so query keys, of course there's nothing there. If I now re-enable that, we now get keys from the SAM hive, because now we've just bypassed the security of the SAM hive, and we can enumerate keys, values, and read out people's NTLM hashes and all that sort of fun stuff. Okay, so let's finish up with the file virtualization bug. And this, in many respects, is kind of like a more interesting one, because it's sort of an interesting race condition. So it turns out that you'd think, well, if you just got one of these files which is just readable, you don't need to do anything special when you read that file, because the existing code will just happily redirect that read request to the right location. No need to do anything. But it turns out you do. So there's actually a specific callback for reading. And what this does is it obviously changes the target file object, but it also captures the real file object and puts it in this completion context pointer, which gets passed back with any filter driver callbacks. And it says, okay, call me back when you've completed. And the reason for doing this is it needs to update certain values in the top level file object. So it needs to update, for example, the current seek pointer, because if it doesn't do that, other pieces of code will fail. It also needs to update this section object pointer, and that's, of course, what I find probably more interesting in this case. So this code is running after the read operation is completed. And the section object pointer is really important because the section object pointer is used by the memory management system in the Windows kernel to map files into memory for memory map file access. And this object pointer structure is allocated by the NTFS driver or by the volume driver, and is usually shared between different instances of the same file. So if you've got a readable file and a writable file, they'll still share the same section object pointers. And when you create your section and you pass it a file handle, it'll extract this pointer from the file object, the top level file object, and use that to construct your section object, which says, these are the virtual memory ranges which contains file data for this file. And it turns out there's a race condition in that read operation because when you issue a read, of course it goes into the NTFS file system, and of course the file virtualization driver can't do any real locking here or can't synchronize the file requests. So while in NTFS we're still performing our read, and bearing in mind at this point the filter has set this context pointer to the read-only file, the real file, if we come along and write to that file, it's going to virtualize it. It's going to create this virtual store file. It's then going to modify the top level file object, redirect its section object pointers, all that sort of stuff, because at that point you want to be able to map that file with write access or whatever you need to do. But of course, the read file operation is still happening at this point. The read file then completes, and of course, if the write is all completed, all the virtual store operations have completed, the post read operation goes, right, okay, I finished reading. I'm going to get the real file object from my context pointer, which is the old read-only file that it passed in originally. And I'm going to copy the section object pointer from that read-only file back into my top level file object, overwriting what that virtualization process had already done. So you end up with a desynchronized section object pointer because you've got your file object pointer which points to your virtual file control block, which does correctly point to the read-write file in your virtual store. However, the section object pointers actually point to your read-only file which you opened. And because these section object pointers are shared between both read and writable copies of the same file, it doesn't matter that that file was opened for only read-only access. You can still create a writable section on top of it to modify it. Now you've got to do some fun tricks to try and make that read operation take a long time. One of the tricks is you can just try and read a massive amount of data, but of course that is indeterminate. There's no way of analyzing that. But I realized that you could use opportunistic locks, and if you see some of my other presentations on this, normally it's used for breaking, like getting a signal when you create a file. But it turns out you can also use this in certain circumstances when something reads a file. You can literally cause the read operation to hang inside the NTFS driver until you close that file, close the original file. The only proviso is you need to pass a special flag to NT-create file. And it just so happened that the Lua virtualization driver was generous enough to pass this flag along. If you open this virtual file with this flag set, it will handily pass it to the real virtual file in the end. And so bypass the op block and allow you to do this wait on a read. So the final thing is we should be able to just demo this. If I just create a simple file, say test.txt, so invert sec. So just a very simple text file. And if I look under, say, System32, license.rtf, open it in Notepad, of course this is now some horrible license file in RTF saying don't do anything you shouldn't do in Windows because it'd be naughty and we'll sue you. So we'll clearly modify that. Hopefully this works. So I've got a proof of concept, and you can just get the proof of concept from the issue tracker. and just compile it and run it on an old version of Windows, and it should all just work. So if we specify license.rtf, and we want to copy test.txt over the top of it, okay. And we apparently failed horribly, which is never a good sign. But no, we did. Okay, so obviously you can't quite see that because, of course, like it can't easily modify it can just completely overwrite the whole contents, but it can't shrink the file because this is actually creating a writable section over the top of the file. But it's good enough if, for example, you wanted to write a DLL to this file, you could just splatter DLL on top of it, and you can actually extend the content. So if your DLL is larger than license.rtf, you can do that. And then there's existing bugs. There's like the diagnostic hub trick, which allows you to basically use license RTF as a DLL and get system privileges from that. And so it all just works. And for all intents and purposes, it has no concept that you've just completely tricked it and overwritten a file you shouldn't have been able to write to. So in conclusion, I'm going a little bit over time, I'm afraid. The virtualization features are great in that when they were originally designed in Vista for back compact benefits, it makes perfect sense. But Vista was introduced in like 2008, right? It's over 10 years old. Why are these features even running on a modern version of Windows? Like, isn't one of the stated aims of backwards compatibility to do something about this and say, like, there has to be a point where we stop supporting these hacks, and actually inserting a driver into every single IO request doesn't seem like an optimum behavior. Maybe I'm wrong. But it's still enabled in Windows 10. It's even enabled in things like special S mode, which is like super secure, we're ultra secure versions of Windows. And you can't run legacy applications because they're not signed by the correct certificate to run them on S mode. And yet we support all this virtualization functionality because hell, why not, right? And pretty much all these bugs, I'm fairly confident, were there since absolute day one in Vista. They've just been sitting there for 10 plus years, and no one ever bothered to look, or if they did look, they didn't bother to tell. And the thing is, this also creates weird, unexpected behaviors in the OS, right? You can trick applications into reading and writing things they shouldn't be able to do. And that is just not really good functionality. So anyway, in conclusion, it's terrible, but it's slightly less terrible than it used to be, but it's still terrible. But anyway, thanks for listening to me at waffle on. I think we probably don't have time for questions as Joe needs to set up, but thanks for listening, and hope you have a good rest of the conference. So, thank you.